At Topaz Secondary, the science teacher, Ms. PRAVINA RATILAL, is preparing her learners for a lesson on the rate of chemical reactions.
There are chemical reactions taking place all around us and within us.
In this introduction, the teacher gets her learners to discuss some of these reactions in their groups. She walks around and establishes their prior knowledge.
When the sulfur dioxide is
Learners will then report their findings to the class.
Our ideas that we came up was the rusting of metals that takes place over a long time period. The second idea that we came up was acid heartburn that people suffer from. There is a certain type of medicine that people take which is Gaviscon. Our third idea that we came up was that coal that is burnt in power stations, and the fourth was that petrol that burns in the car.
Right. These are all simple chemical reactions that we come across in our day-to-day lives. We are now going to discuss the rate of chemical reactions.
The intended outcomes for the learners are to explain the meaning of the term reaction rate, plan how to measure the rates of different reactions by examining the word or chemical equations for these reactions, list some factors which influence the rates at which chemical reactions take place, and recognize the importance of controlling variables when comparing reaction rates.
By the end of the lesson, they should have at least two factors that affect the rate of a reaction, which is concentration and surface area or state of division.
The teacher begins this part of the lesson with a practical demonstration. She pours a solution of lead nitrate into a glass container and potassium iodide into a test tube.
What do you think will happen if I mix these two?
A chemical reaction will take place.
Ms. RATILAL tests their predictions by mixing the solutions.
What happened?
There was a color change.
Do you think this reaction was fast or slow?
It was a fast reaction.
The reactants turned into products in a very short time interval. When a reaction's quick, the rate of the reaction is very, very high. Personally, I believe a teacher demonstration arouses interest in pupils. If I had just told them about the reaction, probably they'll feel it's a myth, it's not real, it's not true. So the demonstration immediately gets their attention, they're interested, they see a color change, and they can identify that when there's a color change, there's a reaction.
The teacher uses another demonstration to add interest to her presentation. She makes sure learners participate by asking many questions.
I have learners from various backgrounds, and everyone doesn't have chemicals. Therefore, I selected a candle because everyone's exposed to a candle. And this candle burning showed them that reactions can be slow. Candle wax reacts with oxygen in the air to form carbon dioxide and water. Notice, I have a symbol recorded in brackets next to each reactant and product. What do you think the symbol L represents?
Liquid.
What does the symbol G in brackets represent?
Gas.
So in our reaction, we indicate the different phases. Was this reaction a fast reaction or a slow reaction?
It's a slow reaction because it took time until the chemical wax occurred.
What will happen to the size of the candle?
Mass of the candle also decreases.
Ms. RATILAL demonstrates that the rate of the reaction can be determined using a formula.
Average rate is equal to change in mass of candle over time. This also means that we can change the rate of a reaction.
The teacher informs the class that sometimes we want a reaction to take place quickly, that is, at a higher rate. Other times, it suits us to have it happen more slowly, that is, at a lower rate. In this demonstration, the teacher presents 2 glasses of water with exactly the same amount of water and 2 effervescent tablets with the same mass.
In the one glass, I'm going to drop a full effervescence tablet. In the second glass, I'm going to use the tablet in a powdered form.
Ms. RATILAL grinds the tablet to a powder and then gets 2 learners to help her time how long it will take for each of the tablets to dissolve in the glass of water.
And will thereafter record her time in seconds on this table.
The first learner places the tablet into the glass of water and begins timing. Next, the powder is placed into the other glass of water and timing begins. When the tablets have dissolved, the watches are stopped.
She tell the class how long the powder took.
16 seconds.
He's going to record it on the table.
The other learner will now give the duration for the tablet to dissolve.
60 seconds.
60 seconds. Record it on the table. Before we go further, we need to check, were the conditions fair so that we can compare this difference in time? Let's check what was the same in both cases.
The amount of liquid.
Color of the 2 liquids are the same.
The mass of the tablets.
Now these that were kept constant, they are called variables. If we choose to, we can make them different, but we kept them constant so that this could be a fair test. So now, what was different comparing the powder and the tablet?
The powder mem was in a state of division.
The teacher explains that this means the surface area of the 2 is different. She demonstrates using a diagram of a cube.
It has 6 faces that are exposed. And the area of each side exposed or each face exposed is side times side.
After substituting 2 centimeters for the length of the sides, her answer is 24 centimeters square. The teacher will now divide this cube down the middle on both sides, creating 8 smaller cubes.
And each one of the 8 cubes will have each side 1 centimeter.
The teacher calculates the surface area to be 8 cubes times 6 sides times 1 centimeter length times 1 centimeter height.
And the total area is 48 centimeters squared.
This figure is compared with the 24 centimeters squared of the larger cube.
So why did the powdered effervescent tablet react faster than the whole tablet?
The powder tablet had a larger surface area.
We may now conclude that the state of subdivision always influences the rate of the reaction. You are now going to do an experiment in your groups to check other factors that influence the rate of a reaction.
In this activity, learners are presented with a worksheet containing clear instructions on how to carry out the experiment. The teacher begins by describing the experiment.
Sodium thiosulfate, which is a colorless solution reacting with a hydrochloric acid solution, which is also clear or colorless. When the 2 react with each other, they will form a milky white substance, sulfur, which is a precipitate.
The first request is for each group to draw a clear X on a piece of white paper. One learner from each group reads the instructions.
When you look into well A1, you must be able to see X on the paper. Use the appropriate label thiosulfate, brackets AQ, to add 1 drop of sodium thiosulfate solution to well A1. Use the appropriate label H2O to add 7 drops of water to well A1. Use a clean toothpick to stir the liquids. Throw the toothpick away. Repeat steps 3, 4, and 5, first in well A2, then A3, then A8.
The attached table shows the proportions of sodium thiosulfate to water in each of the wells. Notice that in each consecutive well, 1 additional drop of sodium thiosulfate is added and 1 less drop of water. When the wells are prepared, the learners start and time the reaction.
Use the appropriate label HCl to add, as quickly as you can, 5 drops of hydrochloric acid to well A. Stir quickly with a clean toothpick and start the stopwatch. Throw the toothpick away.
Learners place the well of the combo plate in which the reaction is taking place above the cross. They will now observe the cross through the solution in the well and record the time it takes for the solution to turn a milky white and for the X to disappear.
Okay. 9 minutes 43 seconds.
A learner fills the time onto the worksheet and each group continues with the remainder of the experiment.
Repeat steps 7, 8, and 9 in well A2 to A8. The same
Learners notice that the time taken for each ascending well to turn milky white becomes less and less. In this group, well 8 is timed with the standard 5 drops of hydrochloric acid being added to a solution with a concentrate of 8 drops of sodium thiosulfate and no water.
The time was 14 seconds.
This is compared with the 9 minutes and 43 seconds of the first well.
Use your results and prepare a graph.
Learners plot the graph showing the rate of the reaction on the y-axis and the number of drops of sodium thiosulfate solution on the x-axis. The formula used to determine the average rate is average rate equals mass of sulfur needed to make the X disappear divided by time. Notice that in the experiment, the same X was used. The same learner looks through the solution each time, and the height of the liquid is the same in each well. Hence, the expression 1 divided by time is a measure of the rate of the reaction in the solution.
The values are very small. So if you go to the table, you will notice your last column has rate, which is 1 over time taken, times 10 to the power 3. Those values will appear on your y-axis.
After substituting the values, the learners plot the graph.
What shape graph did you obtain when you plotted your results?
It's a straight line graph.
Let us check. Were our variables constant? Were they changing?
They begin with all the constants.
Which variables were constant?
The hydrochloric acid was kept constant.
Temperature was kept constant.
The volume of the liquid was kept constant.
The reaction taking place in each well.
The height of each well was kept constant.
Let us now check which variables were changing.
The number of water drops were changing.
The number of drops of sodium thiosulfate.
So which quantity is this related to?
The concentrate.
Now let's check, what does the graph say? As you increased concentration, something happened to this rate of reaction.
It's directly proportional.
What is meant by directly proportional?
As the concentration increases, the rate of the reaction also increases.
So the outcome of your practical is that concentration also influences rate of reaction.
Ms. RATILAL will now assess the learner's knowledge.
If I double the concentration, what will happen to time taken?
The time will be half.
At the same time, if you double concentration, what happens to rate?
It will also double because it's directly proportional.
So if you double concentration, rate will double. If you double concentration, time will halve.
In conclusion, the learners and teachers summarize their findings.
So the factors that affect the rate of a reaction: concentration and state of division or surface. What I've realized from the lesson is that our pupils can do what we expect them to do if we give them the opportunity, enough time, and appropriate equipment and guidance.
Hello viewers at home, we have just watched a video on the rates of reaction. We just want to talk about this with the people at the studio. We have Mike from Wits, we have Dale from Wits, and we have Andrew. Welcome.
Hello.
Thank you. Let us talk about the way in which the lesson was structured. Do you think the lesson that you have just observed was logically structured?
Yes, absolutely. I enjoyed the way the teacher started from where the learners were by asking them some questions, getting them engaged in the lesson. And then she made it very clear what the objective of the lesson was and drew it together with a very nice conclusion at the end. So I think the structure was very good.
And what is the value of actually trying to find out what the learners bring into the classroom?
I think it has to do with the question of relevance. The examples that she got out of them were, for instance, the rusting of a nail. I think rusting is an important process that goes on in industry. I think she talked about digestion and acids and burning of petrol. So these are all things which learners commonly encounter, and so this brings the science to life. That the science is connected to real living. I thought that was good.
And do you think learners do have a difficulty, Andrew, in conceptualizing such a lesson?
Yeah, I think it's we need to appreciate that again. It's very abstract, you know. It's difficult for learners often, and I find that some of the difficulties that would arise, you know, actually were quite well dealt with by the fact that she actually did a session where she determined what their pre-knowledge was, which I think was just excellent, and I think we need to do that to determine where they are, and then do our presentation in accordance to where we determine they are, and actually structure it in such a way that whatever we communicate to them is something that they can understand. But I find that learners do have difficulties with this particular topic. I think many times it's also in the fact that in the way it's presented many a times, and because again of lack of equipment, that sort of difficulties you have in the schools, I think learners have difficulties with the topic. Yeah.
And how do you think teachers should help learners to understand this concept?
Well, I thought the teacher there handled the notion of rate very well. There's a lot of research that shows that learners have a lot of difficulty in understanding the concept of rate. But she got across two very important concepts, and that was the change in mass. In other words, something has got to be changing, and she stressed the division by time. So I think that if the learners had absorbed those two concepts, they would have a much better understanding of the idea of rate by the end of the lesson than at the beginning of the lesson. So the teachers commended for handling that particular aspect well.
At some stage after the prior knowledge or the information from the learners, the teacher actually wrote down those on the board, and then immediately after that, learners were engaged into the practical work. How do you think that practical work was done, Dale?
I think the practical work was lovely. I thought it was good in the demonstration to actually engage learners in doing the stopwatches. Obviously, there aren't enough effervescent tablets for every group to have one, but at least some of the learners were engaged up at the front taking the time. I thought that was lovely. And then the use of the microchemistry kits always works very well. The learners are really engaged in what they're doing. I think it's also good that they have to follow instructions and work through it pretty much unassisted, and that's great.
There was also, Andrew, some demonstration that was done. What do you think the value of that demonstration done by the teacher?
The one demonstration she did was with the color change, which was very dramatic. And I think that sort of thing, you know, look for the dramatic, look for something that the learners can see. I think it's often difficult, you know, for teachers to engage in a lot of practical work. There are time constraints, for example. There's there's limited equipment and material. So demonstrations are definitely very useful. But I think even if you have material and equipment and time, it's good to do a demonstration in order to stimulate interest. And I think she did that very well. And then she went directly from the demonstration into getting them to work in groups, which I thought was excellent, really.
And also in starting that practical work, she started off by actually telling the learners what they're going to do, and then she asked, what is it going to happen? What do you think about her questioning skills?
Her questioning was very good. She particularly drew out of the learners the factors that were being kept constant in any given situation, and that was good.
She asked a lot of questions in the course of the lesson, which I think is great, and her questions were very clear. The learners knew what was wanted of them. And I thought it was also great that she started the lesson with such an open-ended question. So any of the answers that the learners gave had value. They were all good answers, and she showed that they had value by writing them on the board. And I think that helps them to be more willing to give other answers.
Yes. Is there any other thing that you'd like to pick up from the video that interested you?
Well, just a small point, but an important point, and that is that the teacher's talking was very good. She spoke clearly, distinctly, and at times fairly slowly, and so the learners had more than ample opportunity to hang on to every word that she said, and that is important. I think the way we talk to our learners is something which we need to give more attention to.
She was also in the habit a bit, though, of going up at the end of sentences, which leads to the class chorusing an answer. And I don't know that that's always such a helpful way to go about things.
It sometimes
contrasted with her very good use of questioning.
Yeah, it sometimes comes as a habit. Some teachers do it unaware that they are doing. They know it's not supposed to be done, but it becomes a habit.
Yeah, I just want to say, Tembi, that the fact that she used the candle as an example of a reaction that is, slow reaction, I think it was very good. And something else that works very well is to use the peanut experiment. Now, the peanut experiment is one where you basically get a peanut. I'm sure everybody can get a peanut somewhere, and put on a little nail and just light that up. That's very dramatic, and that would contrast very well with a candle, because it sparks and shoots, and it's an exothermic reaction, and it's actually very interesting. The peanut experiment, because also they don't expect for that to happen with a peanut, and they don't expect to get so much heat out of it, a single peanut. So that might be something that perhaps could be interesting as well to look at.
That's all we have time for. Thanks, Mike. Thanks, Dale. Thanks, Andrew. Thanks, viewers at home. That's all we have for today. See you next time. Bye-bye.